say a few words about who he is. He's frequently described as a polymath, I think deservedly so. He's also well known as a public intellectual. He trained as a doctor originally at Oxford University and St Thomas's Hospital in London, and he became Professor of Geriatric Medicine at the University of Manchester and consultant physician in healthcare of the elderly in Salford. In his medical career, he has around 200 publications, mainly in the field of the neurology of old age and neurological rehabilitation. That includes articles in Nature Medicine, The Lancet, and other leading journals. And he's also published 2 major textbooks in these fields. That's only a part of what he's done. He retired from medicine in 2006 to become a full-time writer, though he did remain visiting professor at St George's Hospital Medical School in the University of London until 2008. But in the meantime, outside of medicine, over the last 20 years, he's published fiction, 3 volumes of poetry, and 23 books on topics on a variety of subjects, including the philosophy of mind, philosophical anthropology, literary theory, the nature of art, and cultural criticism. He's also published over 200 articles in Prospect, Times Literary Supplement, and many other outlets. His title today is Killing Time, From Lived Time to, quotes, Little T. Professor Raymond Tallis.
And thank you, Dr. Williamson, for this invitation. And many congratulations. I want to add my congratulations to Andrew on your elevation. I mean, you're a real doctor, unlike me. I got mine an easy way by becoming a medic. PhD, you're a real doctor. My role is to resuscitate time, but in fact, actually what's going to happen, I'm really going to call the ambulance. Brian Fitz is the person going to apply CPR and rescue time from the situation into which it's fallen. Now, since my training is a doctor, it seems appropriate I should begin with a health warning. And what follows is very broad brush. And this is less a reflection of the breadth of my vision than of the shallowness of my understanding. So physicists and metaphysicians, please make sure you've taken your blood pressure tablets. More charitably, my talk is less a scholarly exploration of the overlapping territories I'm going to touch on than an attempt to make a case for future cooperative inquiry between philosophers and physicists. Now, in this respect, I suspect that what I will say will not strike many as novel, because there's already a lot of good work in this area. On the other hand, there are some within physics, and even within philosophy, who feel that philosophers should not speak until they're spoken to, and that their job as philosophers is to act as humble undergardeners to physics. This science cringe, it seems to me, is not an appropriate posture for philosophy. So my main focus is time, which I believe has been treated rather roughly in the physical sciences. At any rate, a widening gulf has opened up between time, as it is experienced in our lives, and time as it features in physics. And this wouldn't be a great cause for concern had it not been frequently suggested that truth is on one side of the gulf, physics, and that on the other side, our ordinary experience, there is only illusion. That there is nothing more to time than what physics tells us. Even that, since some physicists argue that time is unreal, there's nothing to time at all. Now, I want to do several things. To characterize this gulf, to discuss its origin, to look at the basis for the claim that physics is to offer the last word on time, to examine ideas about the relationship between mathematics and reality, which has underpinned many of physics' claims to have the last word on things, and finally to assert in support of a sometimes beleaguered analytical metaphysics that there is a worthwhile work to be done on the very notion of an intelligible account of the world that could allow a re-examination of the relationship between lived time and time in physics, and more broadly, between the world as we experience it and as it is represented in the physical sciences. What I will not be doing is complaining that something is wrong with physics, joining the brigade of oddballs who write letters in green ink to the editors of Nature and of Physics Today, pointing out errors in Herr Einstein's or Signor Rovelli's calculations. Physics seems to be doing very nicely, thank you. And as a grateful beneficiary of its successes, I know it does not require any guidance from a supernumerate medic like me. My problem is not with physics, apart from my own limited understanding of much of it, but with the claim that it has rendered philosophical metaphysics redundant. Let me begin with the gulf between time as we know it from experience and time as it appears in physics. Now, while there is a tendency to think that most of the travails of time date from the beginning of the last century with the special theory of relativity, time was always going to run into trouble when the Galilean Newtonian revolution of the 17th century foregrounded it as an independent, measurable quantity that could be represented by a line. Time became little t, taking its place alongside x, y, and z as one of the four coordinates defining locations in or intervals of space and time. What's more, it became something that, unlike lived time, could be squared or located on a numerator as a denominator, of which more presently. Well, once time became something that could be squared, it was doomed. It was relativity, however, that seemed to deal the most serious blow to time. That was when it lost its distinct identity. And it's scarcely necessary to quote this, surely one of the most quoted passages in the metaphysics of physics. Minkowski's declaration that space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union will preserve independent reality. Time was not the only victim, of course. Space, too, could no longer stand on its own. Temporal and spatial intervals were respectively merely time-like and space-like, since the experience of phenomenal space and time for two observers differs as a function of their relative velocities. Space and time both cease to be absolute backgrounds for observation, both cease to have an in itself independent of observation. As the variable t, time is strikingly impoverished. Most obviously, and most easily taken too much for granted, it is purely a quantitative value. From the standpoint of mechanics, a minute is a minute, irrespective of whether it is a minute of agonizing toothache or a minute of listening to Beethoven. Now, the difference between these minutes is, of course, no business of mechanics. However, failure to register that difference is a symptom of something else that is missing. Indeed, a global absence in the physical world picture. A drastic impoverishment of the world. And to see what it is, let's go back to Galileo and the beginning of the scientific revolution. In his Profession de foi, the Essay, Galileo asserted that philosophy, i.e. physics, is written in this grand book, I mean the universe, which stands continually open to our gaze, but it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It is written in the language of mathematics, and its characters are triangles, circles, and other geometrical figures without which it is humanly impossible to understand a single word of it. Without these, one is wandering around in a dark labyrinth. Those aspects of the world that were not expressible in the language of mathematics not only did not belong to a philosophical account of reality, but were also, in some fundamental sense, unreal, and of course they've subsequently been called secondary qualities. Galileo again. I view myself impelled by necessity, as soon as I conceive of a piece of matter or corporeal substance, of conceiving that in its own nature it is bounded and figured in such and such a figure, that in relation to others it's large or small, that it is in this place or that, in this or that time, that it is in motion or remains at rest, that it touches or does not touch another body, that it is single, few or many. In short, by no imagination can a body be separated from such conditions. But that it must be white, rare, bitter, sweet, sounding or mute, of a pleasant or unpleasant odour, I do not perceive my mind forced to acknowledge it necessarily, accompanied by such conditions. So if the senses were not the escorts, perhaps the reason or imagination of itself would never have arrived at them. Hence, I think that these tastes, odours, colours, etc., on the side of the object in which they seem to exist, are nothing else than mere names, but hold their residence solely in the sensitive body. So that if the animal were removed, every such quality would be abolished and annihilated. Primary qualities such as shape, size, and motion, which are pure quantities, are real and part of nature, while taste, colour, odour are not quite real and not part of the natural world. As the historian and philosopher of science, E.A. Burke, put it, in the course of translating this distinction of primary and secondary into terms suited to the new mathematical interpretation of nature, we have the first stage in the reading of man quite out of real and primary realm. And I'll return to this point when I consider the subspecies of man called the physicist. Let's look a little bit more at how this is expressed in the case of time reduced to a quantitative parameter. The most immediate and striking casualty is tensed time, compared by the philosopher Hugh Mellor to a secondary quality, and deemed by him, by quite a few other philosophers, and by many physicists, as unreal, because tenses are indexed to utterances in which tensed statements are made. Future, present, and past are unreal because they are dependent on conscious beings to plant the flag of now into space-time, into which they can be referred. Now is rejected by physics because it illegitimately privileges a particular foliation in the manifold, with the connected supposition that a single moment in time could be connected on a universal clock. And this is not possible because distant simultaneity is an illusion. It rejects the very idea of a moment in which experiences, and hence observations, and hence measurements, are experienced and thus of special importance. Now this, of course, should be of no surprise, since quantitative science is based on deprivileging actual individual viewpoints, so it cannot find the privileged viewpoint designated by now. Even so, interestingly, Einstein mourned its loss in a conversation with the philosopher Rudolf Carnap. Once Einstein said that the problem of now worried him. He explained that the experience of the now means something special about it, something essentially different from the past or the future, but that this difference does not and cannot occur within physics. That this experience cannot be grasped by science seemed to him a matter for painful but inevitable resignation. Einstein thought that other descriptions, say from psychology, cannot possibly satisfy our human needs, that there is something essential about the now, which lies just outside the realm of science. But he shouldn't have blamed himself for noticing. Now had vanished from physical sciences long before Einstein arrived on the scene. As many, including recently, most vocally and most eloquently, Lee Smolin pointed out, there is no place for now, or indeed for tenses, in the mathematical book of nature. In equations, in lines on a graph, which owe their values to an arbitrarily chosen point of origin, not to an unchosen or lived now, or in pure numbers. In short, what is often presented as a novelty introduced by relativity theory is in fact a consequence of the ascent implicit in pre-Einsteinian mechanics to the view from nowhere and nowhere, and hence from no one. Now, of course, this is a strength. It might be argued that it is the great strength of quantitative physical science, something to take pride in, not to be ashamed of, for now has been exchanged for a timeless viewpoint that enables a view revealing the laws of the most general covariance, which remains constant and is not dependent on individuals. The regulative idea or goal of physical science is a view that captures those features of the world that are invariant despite changes of viewpoint. That is to say, to arrive at the laws which will govern what will be observed as if from a view from nowhere, from anywhere. The apparent contradiction of the view from no viewpoint is possible because it is realized in a mathematical or virtual viewpoint constructed out of numbers, detached from the qualitative actualities of experience. At any rate, there should be no surprise in the fact that when time is reduced to little t, tense is lost. Trying to find now in this realm will be like endeavoring to locate afternoons in the solar system as a whole. The trouble is that loss of tense means that relativity theory cannot, for example, accommodate the contrast between the knowable, determined, actual and unalterable past and the unknown, indeterminate, possible and alterable future. This is central to our own experience of time and cannot be entirely eradicated from a world in which there is change. There may be even more fundamental losses when time is represented quasi-spatially on a four-dimensional graph. In particular, its character of succession. The beginning and the end of the timeline are co-present. Consequently, as Lee Smolin put it in The Trouble with Physics, this puts a block on change. Motion is frozen, and the whole history of constant motion and change is presented to us as something static and changing. We have to find a way to unfreeze time, to represent time without turning it into space. He says he has no idea how to do it and can't conceive of a mathematics that doesn't represent the world, as if it were frozen in eternity. Although the reasons he gives for this, I think, are erroneous. In fact, we can talk about that. But by presenting change as a static life, the change seems to fall out of change, and becoming, added up to a co-present total history of becoming, and hence, as done and dusted, becoming loses its dynamic character. This should alert us to something that has not been sufficiently emphasized, though J.J.G. Smart pointed out 50 years ago. Namely, that the static universe of the general theory of relativity, with an unchanging spatio-temporal manifold, is a kind of truism. Namely, that the sum total of unfolding does not itself unfold, or the sum total of changes is unchanging, or that the sum total cannot be added to. So perhaps there may be nothing more to the basilisk stare of mathematics, terrifyingly shown on this slide, killing time and freezing change, than this. And while we're making deflating suggestions, it's worth noting how in the universe, according to the general theory of relativity, not only does nothing happen, becoming is squeezed out, but space and time, far from being mere receptacles, are actors in this drama in which nothing happens, a role hardly worth joining equity for. Enough of the cheap shots, there are serious problems. The point is that Smolin is correct in looking beyond contemporary physics for chronoscience. It is at the heart of what we might call the Galilean project, which aims to reveal the essence of the natural world as the expression of the covariance of quantitative variables. And this is made particularly clear by Carlo Rovelli in an essay entitled Forget Time. He argues that in order to build a quantized theory of gravity, where this notion does not appear at all, we must forget time altogether. He does allow situations where time might reappear, rather as temperature, which boils down to the velocity of molecular movements, appears at the thermodynamic level. But at the most fundamental level, he argues it will be absent. Mechanics will become a theory of the relations between variables, rather than a theory of the evolution of variables in time. But he too seems to believe that this is how it's been all along, at least since the era of Newton. He supports his case against the fundamental reality of time with several arguments, but one is a bit surprising. We think we are measuring time as if it were some kind of stuff, but all we're doing is comparing clocks in a closed circle of mutual validation. Galileo used his pulse to demonstrate that the swings of the chandelier were isochronous, and then used the chandelier to time his pulse. And that really is how things have always been. Rovelli surprisingly overlooks that this apparently closed circle, which suggests that we have no way of checking that our clocks are in time. This apparently closed circle is actually broken in two ways. There is first of all the increasing consistency of clocks. Atomic clocks are more in sync than pendulum-based clocks. But more compelling than this is the discovery of laws which enable periodicities to be predicted independent of measurement. There is a network, a clockwork mesh of laws of a precision that goes beyond actual measurement. That's something to which I'll return. Which is why we can be sure, or it makes sense to be sure, that a cesium clock is a more accurate measure of time than a water clock. The important point, however, is that for Rovelli, and for many others, such as Wheeler, DeWitt, the famous equation, if time drops out of the equations, it's not real. For me, this simply demonstrates that once time is presented as little t, its days are numbered. Now, it's difficult to know how seriously physicists take the death of tense, or even of time. Some do seem to be persuaded that when we arrive at a complete account of the physical world, of which, according to them, we're entirely a part, there will be remarkable existential implications. Paul Davies, for example, argues that physics may lead us to a place beyond lamentation, the sunlit upland of no more tears. And what if science, he said, were able to explain away the flow of time? Perhaps we would no longer fret about the future or grieve for the past. Worries about death might become as irrelevant as worries about birth, the Lucretian consolation. Expectation and now nostalgia might cease to be part of the human vocabulary. Above all, the sense of urgency that attaches to human activity might evaporate. It's astonishing and rather touching that this hope should flower in what must be the stoniest of stony soils, in an intellectual landscape dominated by the ultimate constituents of mass energy portrayed in equations linking values of variables. Or indeed that physics, which bypasses the existential reality of time, indeed of the human subject, should be claimed to have such positive existential implications. but this provides a useful entree into the core concern of this paper. How to interpret the gulf between time and physics and time and life. And there are two ways of interpreting this gulf. One, option A, is to adopt a scientific view, according to which, notwithstanding what our experience tells us, physics is the definitive guide to the metaphysics of time. If physics cannot accommodate tensed time is unreal, and the difference between past, present, and future is a distinction which we'll learn to live without once we see the world aright. Or more radically, if, as Ravelli hopes, time drops out of the equations, that because they can do without the time variable in the theory of everything, it drops out of the universe. If physicists can forget time, it follows that the universe is timeless. The other, option B, is to argue that since there are certain undoubtedly real aspects of time that are beyond the reach of physics, it's physics, not our lived experience, that is sufficient. What reason might we have for bowing to the authority of physics over that of everyday life and choosing option A? Well, we listen to what physicists have to say because physics works. We accept the idea that a mathematized version of time as little t captures the essence of time because this version is delivered so much. The incomparable predictive and technological powers of physics seem to furnish incontrovertible evidence that it produces not merely models of reality, but reveals what is really real. As Hilary Putnam expressed it, scientific realism is the only philosophy of science that does not make the success of science a miracle. How could physics be deficient if it gets so spectacularly right? Since the power of physics lies in the employment of mathematics, some have found it difficult to resist the Pythagorean conclusion that reality is mathematical. That, for example, time in itself, if it exists at all, is the pure quantity little t. It is the kind of thing that indeed can be squared, slipped under, e.g., distance as a denominator, or even attached to space via the square root of -1. It is irrelevant that lived time does not lend itself to these mathematical operations. Alice in Wonderland might say, fancy multiplying an afternoon by itself, but the physicist would just shrug his or her shoulder. Time can be subjected to all these indignities, of course, because it is stripped of occurrences, of actuality, of reference to any particular now or any particular time. It is a pure quantity. Should we not then wonder in what sense time transformed into little t, a contentless individual, is time at all? This opens on to the larger question of adopting a purely quantitative theory, of the general justification for adopting a purely quantitative theory of the universe. We need, in short, briefly to examine the relationship between mathematics and reality. Many, perhaps most of you, will be familiar with Eugene Wigner's 50-year-old paper, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Wigner noted how the mathematical formulation of a physicist's often crude experience leads in an uncanny number of cases to an astonishingly accurate description of a large class of phenomena. And R.W. Hamming, in a paper whose title consciously echoed Wigner, noted how constantly what we predict from the manipulation of symbols is realized in the real world. One of the most familiar examples of this unreasonable effectiveness of mathematics is also one of the most striking, Newton's law of gravitation. The numerical coincidence that Newton noted between the speeds of falling bodies on Earth, the parabolic pathways taken by thrown rocks, and the elliptical orbit of planets led to a mathematical law with a universal application. As Wigner put it, the law of gravity, which Newton reluctantly established, and which he could verify to an accuracy of about 4%, has proved to be accurate to less than a 10,000th of a percent. And he makes a general point. While science is composed of laws which were originally based on a small, carefully selected set of observations, often not measured very accurately, these laws have later been found to apply over much wider ranges of observation and much more accurately than the original data justify. Not always, but often enough to require explanation. I'm sure you could come up with dozens of even more spectacular examples, ranging from the use of tensor calculus, developed in complete ignorance of any application you might have in general relativity, to another instance cited by Wigner, the importation of matrix algebra into quantum mechanics. It has proved extraordinarily powerful in understanding and predicting to 1 part in 10 million what is going on at the subatomic level. It seems then that there is more to mathematics in physics and the reduction of the world from qualities to quantities than a convenient notational system, even if we extend the notion of convenience to encompass Poincaré's idea of simplicity. The claim of mathematical physics to tell us something about fundamental reality clearly can't be dismissed by what Whitehead called the muddle of importing the mere procedures of thought into the facts of nature. Should we therefore conclude, along with some physicists, metaphysicians, or philosophers of science, that mathematics does not merely offer the most effective ways of modelling the universe, but that it is the most faithful portrait of what it really is, so that observing the behaviour of little t in the mathematical world of physicists is to see time itself. That, as Lord Kelvin asserted, mathematics is the only true metaphysics, with the implication that the rest is bunkum. Shall we conclude, to repeat what Putnam said, scientific realism is the only philosophy of science that does not make the success of science a miracle, replacing in this case scientific realism with mathematical realism? Or should we more radically accept the Platonic claim that mathematical objects, numbers, sets, figures, even items like the square root of -1, are real entities? Or most radically of all, embrace an industrial strength of Pythagoreanism and conclude that all is number, so that reduction of time to a pure quantity is to reveal its true nature. The notion of all is number is a view advanced by Max Tegmark, already referred to this morning, in a recent book, Our Mathematical Universe, My Quest for the Ultimate Nature of Reality. What he calls his mathematical universe hypothesis, or mathematical monism, denies that anything exists other than mathematical objects. Even conscious experience is composed of mathematical, self-aware substructures. This leads him to some strange conclusions. For example, that if something is mathematically consistent, it exists. All possibilities that don't break the laws of mathematics are as real as the ground under your feet, indeed more real. An even more challenging claim that the mathematical structures of which the universe is composed are sets of abstract entities with relations between them, thus giving sets, abstract objects, and relations ontological priority over members of sets, concrete items, and relata. He also arrives at the conclusion that mathematical structures are timeless, and so time is an illusion, as is change. So there'll be nothing in this book, by the way, that will cause us to change our mind. Leaving aside the awkward fact that the title of his book contains terms, Our Mathematical Universe, My Quest for the Ultimate Nature of Reality, and so on, that his thesis cannot accommodate, the easiest way to see what is wrong with this extreme mathematical realism, according to which mathematics is not merely the best guide to reality, but is reality, is to reflect on how Tegmark and other Pythagoreans arrive at their self-contradictory conclusions and examine exact examples. Consider an equation with which some people in the room may have a rushing acquaintance, E equals mc squared. As with any law, it describes a mathematical relationship between values of variables, energy, mass, that have no other properties than quantity. More generally, physical laws are about covariance of quantitative parameters. The energy in Einstein's equations is not warm or bright or noisy, and the matter is not heavy or sticky or obstructive. The world of physical laws, which enables predictions of quantities, is a world of quantities without qualities. Light, by the way, there is represented solely by speed extracted from it and squared. This, as we've seen, is not an accidental omission. Physical reality is thought to be comprised of primary qualities such as size, shape, location, and motion, which can be expressed without remainder in mathematical terms. Secondary qualities resist being mathematized. The mathematics of light does not get anywhere near the experience of yellow, nor does the mathematical description of patterns of nerve impulses reach pain. Now, this may be seen as evidence that neither the colour nor the pain are really real, though it might be difficult to sell this claim to the man looking at a daffodil or a woman with toothache. This may not persuade those who still insist that the actual contents of our consciousness are an illusion, or in some way ontologically shabby, suspect, or second-rate. But there is a more fundamental omission: actuality. Physical laws describe the most general relations between patterns of change. A pattern of relations between events or objects is not an event or an object. these are singulars. A pattern of relations between events or objects is not an event or an object, which are singulars, realized through the qualities which characterize them. And this is more than a truism. It says more than that a summary leaves out things out, or a classification of something as red does not capture its particular kind of red, or the generalization skip over particular details. A world without qualities, consisting solely of mathematical patterns or structures, is a world without actuality. Wigner moved in the direction of this criticism when he remarked that the laws of nature are all conditional statements, and they relate only to a very small part of our knowledge of the physical world. Thus, classical mechanics, which is the best known prototype of physical theory, gives the second derivatives of the positional coordinates of all bodies on the basis of the knowledge of the positions, etc. of those bodies. And here's the killer line. It gives no information on the existence, the present positions, or velocities of these bodies. Elsewhere, he summarizes these aspects of the physical world that lie outside the laws in the standard way as initial conditions. These initial conditions would include the fact that there is something rather than nothing, that there is stuff, that there are certain constants that have certain values, that there is one set of laws and not another set, and so on. In short, they have little to say about actualities, which are all outside of the laws, being those conditions on which the life are operated. More laws will not dispense with the need for extra-legal initial conditions upon or within which laws work. If you reduce the world to quantities, you lose the world. So from the fact that mathematics predicts quantities, it does not follow that quantities are what things are, what reality consists of, or the sum total of that which is real. Not everyone has been fazed by this, and in fact the latter stuff has been celebrated by some writers such as James Layman, of whom much has been spoken already, and who spoke last year. He defends a trademark like ontic structural realism, according to which reality is a general structure, and indeed the mathematical structure of the world is that which is most truly real. Everything else, to vary the title of his book, must go. For the rest of us, general structure without particular content is not merely impoverished, it is either an impossibility or nothing at all. Asserting the priority of structure over objects, the inevitable consequence of reducing the world to primary qualities is to assert the priority of an abstraction over that from which it may be abstracted. Likewise, real patterns that are not patterns of, real patterns have to be patterns of something other than a pattern. Mathematics, which in physics describes general relations between changing quantitative variables, ultimately describes relations without relata. Pache Quine, to be is more than to be the value of a variable. Existence, actuality, reality is more than a quantity predicted by a law of covariation. And it was this that prompted Bertrand Russell, who after all was a strong advocate of science and no slouch when it came to mathematics, to pass this verdict. Physics, he said, is mathematical, not because we know so much about the world, but because we know so little. Only its mathematical problems that we can discover. This is not right, of course. We can discover the non-mathematical properties of the world, colours, pain, smells, and so on, by opening our eyes and following our noses and attending to our sensations and picking things up and doing things like imagining what somebody else is feeling and so on. But we know what he means. When we want to look past the deliverance of our experience, the most powerful tools are mathematical. But unfortunately, they can give only mathematical answers to our questions about a fundamental reality which is more than mathematical. What is more, the world of pure quantities, of primary without secondary qualities, is a world without the possibility of physics, because it is the world without the possibility of physicists. Or, indeed, without the possibility of a community of minds extending over space and time that's been involved in developing the view of physics that we call, the view of the world that we call physics. The world in which the physicist lives is, of course, made up of secondary qualities. She is always steeped in intense time. Her whole life is located in a privileged foliation of the manifold. Otherwise, she would not be able to make appointments to meet other physicists, indeed decide to do something now, or indeed to take credit for work done in the past, or live as though time was not only real, but also distinct from space. The gap between home and laboratory is different from the interval between the beginning and end of an experiment, even though the line that connects the two will be one that cannot separate space and time. But there are, however, more intimate and profound ways in which doing physics and being a physicist are at odds with a mathematical world picture of pure quantities. The path to the kind of Pythagoreanism that I just discussed is smoothed by closing the gap between the physicist and the physical world. And this is effected by a conflation of several terms: observer, recording device, the act of measurement, measured quantities and numbers. Although relativity theory, for example, seems to put the observer at the very heart of physics, it's difficult to be sure at any given time what the observer, he, she, or it is. He or she can be replaced by a clock or some other recording device, with the process of reading the clock being pushed off stage, as if a clock by itself can tell the time, even if there were no one to tell it to. Of course, any source of equally spaced periodic events can be a clock, so long as there is someone using it to measure time. In the absence of a user, however, such sources are not clocks, but this is often overlooked. One example will have to suffice: Paul Davis's assertion that some particles, such as muons, have a built-in clock because they decay with a definite half-life. The idea that physical systems by themselves can qualify as clocks is just one symptom of the tendency effectively to marginalize, eliminate, or elide the observer, to do away with the most awkward feature of this awkward entity. The clock itself is then effaced in favour of measurements made with it. The measurements boil down to numbers which assign values to variables, whose covariance with other variables is ultimately represented in laws of the highest generality, such as the field equations of general relativity. Now, it might be argued that far from eliminating the observer, a theory such as general relativity confines itself to and captures the sum total of possible observations, describes what observers would measure or would experience in all possible circumstances. What we see, in other words, it might be argued, is not the loss of the observer, but the transition from the individual observer to the most general observer, capturing what is invariant under the variations in recordings made by observers in different frames of reference. But this defense doesn't hold up. The permanent absence of any particular observer, replacing her by clock readings that are read by no one, is the absence of all observers, or what amounts to the same thing, an observer translated into a frame of reference defined entirely numerically. This is revealed with remarkable clarity in the critique of the thought of Bruno Latour by Alan Sokal and Jean Brickman, and I single it out only because I came across it recently and cried bingo. In pedagogical presentations of the theory of relativity, Sokal and Brickman say, a frame of reference is often equated loosely with an observer. More precisely, a frame of reference can be identified with a set of observers, one placed at each point in space, all at rest with respect to one another, all of which with suitably synchronized clocks. So far, so good. But it is crucial to note that these observers need not be humans. A frame of reference can be perfectly well constructed entirely out of machines, as is nowadays done routinely in high-energy physics. Indeed, a frame of reference need not be constructed at all. It makes perfect sense to imagine a frame of reference attached to a moving proton in a high-energy collision. In other words, a frame of reference is not a place where someone is located, but, for example, a numerically defined space around the 0, 0, 0 reference point, which somehow manages to be a reference point without there being anyone to refer to it. And that reminds me of something that Andrew kindly referred to when I was talking about the peculiar notion of a point. What is most peculiar about the idea of a point is that it identifies a location in space without occupying space, because it's dimensionless. How does it do that? It does that because it's got offstage support, basically the axes of a coordinate system, and they are imported. So the idea of a point is in fact something that it's actually parasitic. It's a spatial parasite. It requires, as it were, its location to be borrowed from somebody else, something else. Of course, it's perfectly true that what is independent of the observer are the laws that conserve when we move from one frame of reference to another, as illustrated by the equations used for translating between sets of coordinates. And there may be no human presence in a particular experiment. The apparatus is set going, and everyone goes on to the pub to receive the readings later. However, the readings have to be read to count as readings, so the conscious observer can be postponed, but not cancelled. Without such an observer, A proton, indeed any material object, cannot be a frame of reference, or indeed count as a physicist. The ascent from individual conscious observers to general laws does not license pulling out the ladder after the general laws are arrived at to suggest that the universe, including physicists, can do without individual conscious observers, or equating observers with, say, clocks that any periodic events can qualify to be. Clock readings can be reduced to pure quantities only by thinking of physical systems in the absence of observers as clocks in themselves. By this means, it's possible to conceal the fact that observations, measurements, recordings are a distinctive subset of events, and these cannot be accommodated in the mathematical world picture, even though the results of those observations, of course, can be. A purely mathematized view of the world, in short, extrudes or excludes the physicist as observer, as that in virtue of which there are points of view from which observations are made, and necessary now and a here in which actual observations are carried out. Without this flesh and blood conscious creature, however, with secondary as well as primary qualities in a world which also has secondary as well as primary qualities, there will be no actual frames of reference, and hence nothing to flesh out the general mathematical relations connecting frames of reference travelling at different relative velocities. At any rate, a purely mathematical world picture could not accommodate anything like a physicist making observations from a particular frame of reference at an actual time and place. And of course, without physicists, there can be no physics. While the physicist as observer is not a social being, is neither a man nor a woman, he or she has to be realised in social beings. I was tempted to respond to this by saying, of course, observers and so on are pushed to one side, and the particular sociology of the social being who is the observer is entirely irrelevant. Physics aims to transcend the parochial world of individual beings. That's its whole point of why it's so powerful. And this has some truth, insofar as we've noted much human benefit, practical or cognitive, has come from physics. But it doesn't follow that what has been left behind is an illusion. Otherwise, physics itself and physicists will be illusions, and it's easy to see why this cannot be the case. Put another way, a general world picture does not and cannot disprove the reality of the particulars upon which ultimately it's been arrived at, to which they apply. Without observers that cannot be accommodated in a mathematical account of the world, the kind of characters who make observations here and now, there can be no mathematical account of the world. The key point is this: the world of mathematical physics, unlike that of any living creature, including the physicist, is a world without qualities. It is a world in which time, if it exists at all, has no characteristics such as tense, or indeed even a clear distinction from space. This lack of qualities in the mathematical world picture caused, surprisingly perhaps, some discomfort to Richard Feynman. In a late lecture he said, the next great awakening of the human intellect may well produce a method of understanding the qualitative content of equations. Today we cannot see whether Schrödinger's equation contains frogs, musical composers, morality, or whether it does not. This perhaps is less supportive than might initially appear. After all, he assumes that it's equations, which are essentially quantitative, that are actually repair the deficiency. But it will be obvious, I think, from what I've said, that better equations won't restore qualities to the scientific accounts of the natural world. But one should be grateful for at least a partial acknowledgement of the problem from some eminent source. This seems at least halfway to the intuition that, as Plotinus said, to measure something is not to grasp at something. Or at very least, the quantity of x is not the same as x, or no real thing, time or space, boils down to quantity. Where do we go from here? I want to end by making brief observations about the challenge facing those who want to make better sense of time that takes account of what physics has discovered, but doesn't dismiss everyday experience, which, for example, justifies a different attitude towards yesterday's dental appointment, or tomorrow's, or to the fact that experiments are always done now. It is obvious that developing a metaphysics of time that does even-handed justice both to well-founded physics and to those inescapable temporal features of our lives that lie beyond the reach of physics will require a profound rethink. We will need to try to cross the distance between lived time, which is distinct from space, has a character of succession, is tense and belongs to the world of quantities, and little t, which is a point, or part one, a line or an aspect of one, or a number that belongs to the universe of pure quantities. I think I've lost my sound. Can I still be heard? Take our lantern side. Still audible? Yeah. Good. At the very least, we need to make more careful sense of that subset of events in the universe that are observations. More particularly measurements of events in the universe, taking note of Venus observation, but that is not at all natural. That is not at all natural that the laws of nature exist, much less that man is able to discover them. Such a rethink won't be possible unless there is much more continuing open-minded dialogue between physicists and philosophers. It will be difficult for all sorts of reasons. Most importantly, the one noted in this passage that will be familiar to at least one member of the audience. This is a realm in which it is difficult to draw a sharp distinction between metaphysics and physics. It can be difficult to know what is a matter of straightforward empirical fact and what is a matter of legitimate philosophical disagreement. How much philosophy is built into the usual understanding of physics. We're travelling through border country and will need to keep our wits about us. To which I say, Amen. To vary Douglas Adams' aphorism, time is mysterious, but lunchtime, which you're eagerly awaiting, is doubly so. Thank you for your attention, or at least the courtesy of simulating that. Thank you.
Okay, we have about 10 or 15 minutes of questions.
Thank you for your talk. It was very stimulating, and I hope I live up to your billing later on. I'm wondering if it's possible that a substantial part of the problems that you're diagnosing are maybe related to modern philosophy of mind. It's tempting to assimilate contemporary views with those of Galileo and Descartes, for example, but they would clearly make have a different status for persons that contemporary people are often less likely to make. Is that one way to address some of these problems? Maybe it's problems in physics, maybe it's philosophy of mind, or maybe it's both.
I'm not sure we can lay much of the blame at Descartes' door, having sort of clearly separated mind and so on from the physical world examined by the physicists of his day. I think there's a greater problem in our contemporary philosophy of mind. You probably know one of the leading orthodoxies in the philosophy of mind is the identification of even phenomenal consciousness with neural activity in the brain, i.e. with biophysical phenomena in a particular organ. And I think that is, for many people, it seems to justify assimilating the physicist into the physical world, because the physicist then becomes part of the physical world. It actually then makes it extraordinarily difficult to understand how the physicist can be offset from the physical world in order to examine it, make observations, and arrive at theories about it. So I think there's more problem with contemporary philosophy of mind, I think, than there was the philosophy of mind going on Descartes' time. And indeed, Galileo, he was only sort of half, as it were, distancing himself from quite a lot of Aristotelian and theological notions of the person. After all, he separated the role of, as it were, scientists to see how the heavens go, and the role of the priest to see how to go to heaven. Quite a sort of important distinction.
There was a question up there. Is there a question? Other question.
Thank you very much for a wonderful talk. This issue with relativity, I think it was betrayed, because I think initially the philosophical insight was remarkable. I think Einstein tried to break out of the Newtonian box. And I know it's a matter we've discussed before. The essential insight is that time and space are not the most fundamental things. Light is more fundamental than space and time. But somehow when it became mathematicized, put into the Minkowski equations, something was frozen again. And it's almost as if the initial insight of relativity was actually quite philosophical. Then it was put into a form that betrayed its initial insight. And I often come across people now who tell me that because of relativity we live in a box universe where time and space are equivalent. Actually, when you trace out what happens to an event, it's not the case. That's not the only way of interpreting relativity. But it's interesting again that mathematics portrays the more fundamental insight, and this is something that Lee Simone picked up in his talk. So relativity doesn't have to do what it has in practice done in terms of people's imagination about the universe.
I think that's very true, and there's also a certain amount of evidence in the application of Ernst Mach's notions about, his philosophy of science. I know there are people in this audience who know much more about philosophy of science than I do, but it just seems to me that clearly relativity theory came in part from the acknowledgement that it was difficult to assign meaning to something that wasn't actually translatable into experience, i.e. observation. And that's fine. The problem is then you forget the observer, and you cannot translate the observer into an observation, and I guess that's where the problems came, even before all the further problems of applying Mach's theory when it came to quantum mechanics.
I suppose
I like very much your suggestions towards the end that one should analyze the role of the physicists within physics and how observation works and so on and so forth. But I wasn't quite clear whether you thought that's something that should and could be done with the toolbox of mathematics and physics, or whether there's an in-principle difficulty in doing that. Trivial example, primary, secondary qualities, color. Yes, just looking at the initial frequencies or whatever will not give us back the picture of the phenomenological picture of color. But if we look at the physiology of color vision, we get a much richer picture. Can we reconstruct? Should we and can we reconstruct the secondary qualities using the same tools of mathematics and physics, or is there some difficulty of principle?
I think there's a difficult principle. I mean, I speak now as somebody who hasn't got a dog in the fight, as it were, neither being a philosopher nor a physicist, being a medic. But it seems to me that what philosophers would bring to the party would be two things, probably many other things as well. Clearly, conceptual clarification. I mean, I generally feel that when we have an incredibly powerful theory like quantum mechanics, in which I've been a beneficiary in my everyday life, laptops and so on, which is actually unintelligible, and let's be honest, it is unintelligible, and unintelligible in principle, probably not merely in actual, so far. There is potentially a role to say, well, let's look at the concepts that have been fed in, let's look at the metaphysics, as Catherine was saying in the quote, let's look at the metaphysics that's come into, that's slipped into the physics. And the other is perhaps, as a philosophers of science, might sort of look at the etiology of the problems, we would say in medicine. How did we get to this spot? What has led us down this particular track? So I think there's some very important contributions there. And then perhaps sitting together and literally just hammering out and saying, what would be a really satisfactory theory of understanding of time? Not even sure I know what I mean by an understanding of time, but at least, I can see what you bring to the party, and see what I bring to the party. Is there some, as it were, vanishing point where our two cognitive contributions converge? That is not accidentally vague, because I have a little bit of uncertainty.
Thank you. I think that you made some very important deep questions about the relationship between mathematics and physical reality. But I just wanted to resist something more specifically you were pressing about time, and this idea that if we don't have becoming or a theory, as philosophers would call it, or some kind of mysterious tense in reality, then somehow everything's frozen and static and we can't distinguish the past from the future. I mean, different things happen at different times. Lunchtime's ahead of us, and the early talks are behind us now. This, to me, looks like change, different things happening at different times, and there doesn't seem to be anything sort of frozen or static about it. So I do want to resist this idea that if we have the death of tense, as you put it, then we automatically have the death of time, as if everything then is automatically happening in a big kind of mess at the same time.
I agree with you. I don't think we need to be an atheist to accept the reality of change. But I think the bits of time that die and the bits of becoming that go and the bits of change that go, they go in sort of different ways and in different areas of physics. I mean, there is one interpretation of general theory which actually kills time and stops becoming. One interpretation, not everybody agree with it. And there is a simple interpretation, Jack Smart's rather teasing interpretation of that. So I agree with you. I mean, you can be a B theorist and still have change. But I think within physics, there is different degrees, it seems to me, of chronicide and changeicide. And some physicists clearly feel there's nothing important or real to tense. Others feel there's nothing important or real to time itself. Or the sooner we get our act together, the sooner we get rid of time. And we need to disinfect this from our equations. And some of those, famously people like Hans Reichenbach, will say the conclusion that is there's no becoming. But I agree with you. I think these are independent claims. Questions?
I assure you I'm not just asking this because the microphone was very nearby. And I apologise that this is an inchoate question. But the discussion of tense and the fact that little t seems not to have it has got me thinking about other properties which we measure quantitatively but that have other aspects to them, such as weight, for example. I mean, it is the case that I make my observations from this place and at this time. It is also the case that I make these observations at my current weight and at my current temperature and so on. I somehow feel more nervous about the fact that modern physics throws away the context of the time and place of observation than I do about the fact that modern physics throws away the weight or the temperature of the observer. And I suppose my question is, should I? And is that differential nervousness just a remaining ghost of the primary-secondary quality distinction which I should try to expunge?
That wasn't at all an incorrect question, it was a fantastic one. It just seems to me that clearly people, some physicists have got very worried about now. Quite a few physicists have been less worried about here, actually, the loss of here, surprisingly, although that's just as grievous a loss. But it's clear that in order to make a physical observation, you don't have to have a particular weight, but you have to have some weight. And you have to be of a certain age, and so on and so forth. So I guess all of these things is that, why have we got so worried about, as it were, here and now, and less worried about whether you have a certain weight? It seems because physics is always dealing with space and time. I know it's also dealing with mass, but not, as it were, as global parameters. So that's why the failure to find tense time or time indexed to an observer seems more grievous than the fact that we don't acknowledge that the observer also must have a weight, and must be a man or a woman or whatever. Is that a reasonable answer to a...
Yes, perfect, thank you.
I felt the question was better than the answer, actually. But
Okay, I've been told that we must finish on time for lunch. So there's lunch now, then we restart here now. And let's say thanks very much.
I'd like to remind you, if you want to book a taxi,